So we are recording, and so this will go for like 2 hours. We'll probably take a break halfway through. And if you need to leave at any point, I will post this video, so no worries. Okay, so I tried to make these problems pretty similar to what you would see on an actual Darrell exam, but I haven't seen the actual final exam, so it's just my best approximation. I'm hoping it gets close, but I can't promise that. So let's go ahead and think about some of these problems. So he likes to bring this 10 to the x graph back into play at final time. So let's look at part A. Part A is asking for the log of 5 to the negative 8. Okay, so the way I would do this is I would think, first of all, I can do some log rules. So before I even think about the graph, come down here and I'll say, well, I know log of 5 to the negative 8. I can use the good old, what do you call it? Maybe power rule for logs. Bring that power out front. So that's just negative 8 log of 5. Maybe I'll make a note. That comes out front. Cool. And then from there, we have to figure out what log of 5 is. Okay, so for that, we can use this graph. And maybe I'll zoom out a little. All we really need to do here is, well, log of 5. Log is the opposite of 10 to the x. It's like the inverse function. So instead of plugging 5 in for x, I could plug 5 in for y. And okay, so that's right here. And then we'll trace that across to see where it lands on the graph. And lo and behold, it's actually a very nice answer of about 0.7. Okay, so this is negative 8 times 0.7, which if you work that out, what's that, negative 5.6, I think? Assuming I still know how to multiply. Okay, cool. So hopefully that one's not too bad. Any questions about that before I do part B? Feel free to speak up at any point. We only have about a dozen people here, so it's fine to interrupt. Okay, so for this one, I'm looking at this and I'm saying, okay, log of x equals negative 2.1. Okay. Unfortunately, I can't really do a whole lot with the graph yet because it's a negative number. So does anyone have a suggestion of what I might try?
Can you, oh, sorry.
Wouldn't you take the power of 10 to both sides?
Cool, I like that suggestion. So we'll do 10 to both sides, and I'll just write out all the details when we're doing this. Okay, and whenever I have 10 to the log x, I kind of like to think about those canceling, and I'm just left with x because they're inverse functions. Okay, so x equals 10 to the negative 0.2, or negative 2.1. And then I want to think, wait a second. Yeah, okay, so I want to figure out what 10 to the negative 2.1 is, right? I mean, this is a good answer, but I want to get a decimal approximation for it. So I have this graph of 10 to the x, but again, I can't plug in negative 2.1, right? What could I plug in instead? Actually, there are a couple ways to approach this, but
0.1 or negative 0.1?
Yeah, either one of those are going to work. The thought process is, well, I could split this up in a couple ways. I could split it up as like 10 to the negative 2 times 10 to the negative 0.1. And then you could go from there. 10 to the negative 2 is just 1 over 100. And then 10 to the negative 0.1 is 1 over 10 to the 0.1. Okay, so sorry, that's kind of small. And then that piece in the denominator I could figure out from the graph. Okay, I want to show an alternative really quickly. So alternatively, I could have done something a little different. And I think I like this way a little bit better. I could have broken it up as 10 to the negative 3 times 10 to the positive 0.9. Okay, the other way is correct, but I like this way because then I'm just dealing with a positive exponent here. And that's the same thing as before, because if I were to add these exponents, negative 3 plus 0.9 is in fact negative 2.1, like what we started with. But it's not a big deal if you don't think about that. The other way works just fine. Okay, so this is 1 over 10 cubed times, let's figure out what this is. So 10 to the 0.9, I can get by just plugging in 0.9 right here. And okay, maybe now you see why I prefer this, because it kind of gets you almost exactly 8. So that's a nice number. I'll say maybe like 7.9 or something. Okay, so we'll say that's 7.9. And so that just ends up being 7.9 divided by 1,000. So move the decimal place a few places. And is that correct? -3, yeah, that should be fine. Cool, and maybe I'll check my answer. Yeah, so that gets pretty darn close. The true answer is like 0.00794. Okay, so that looks good. Any questions there? It's just a note to myself. That's why I can do that. All right, cool. And then let's think about part C. Okay, so part C, find the slope of the graph near x equals 0.4. Okay, so x equals 0.4. Trying to find the slope at that point, but I can't do that exactly. If I knew how to take the derivative of 10 to the x, I could, but we only know the derivative of e to the x. Okay, so what I might do is I might instead take some points nearby. So let's say I took this point and this point. So that's 0.3 and 0.5. Or maybe you want to get closer and do like 0.35 and 0.45 to get a better approximation. I think this should work okay. So then I'm looking at the secant line, and the slope of that secant line should be pretty darn close to the slope of the tangent line, or the slope of the graph. Okay, so let's figure out what these y values are corresponding to these x values that I'm plugging in. So again, these are pretty nice. So that's 2, that's maybe 3.2 or something. Okay, and yeah, let's just work out C up here because I ran out of room. So the slope of the graph, let's just label these 2 points. So x1, y1, we'll say was this point. So that's 0.3 comma 2. x2, y2 is 0.5 comma 3.2. That's that point. Okay, and from there, all it's asking for is slope. So slope is y2 minus y1 over x2 minus x1, which in this case, that's 3.2 minus 2, 0.5 minus 0.3. So 1.2 over 0.2 gets you what, 6? So 6 is a decent guess. Turns out the actual one is 5.78, the exact slope. So you might get closer if you plug in numbers closer to 0.4. But there we go. It's kind of clunky working on a tablet, so that's my best guess. Any questions about that one? Okay, cool. I think I'm going to save this document after, so I won't erase anything here. Let's go to the second page. So the second page is a bunch of derivatives, including a second derivative. And I thought this one was kind of a tricky one. It's kind of clever, kind of tricky. If any of you have taken a calculus course before, you might look at this thing and think quotient rule, but that is not something we've learned, as far as I'm aware, in Daryl's class. So we're not going to do that. We're going to try to do this all algebraically. So let me write down part A. If I just plug in f and g, 2x cubed plus 10x squared. Okay, so that's f, and then g is this. And I'll ask for some input from you guys. Feel free to use the chat box if you prefer. But does anyone have a suggestion what I could try here if I don't know this mystical thing called quotient rule?
Factoring.
Yeah, I should be able to factor. So first of all, each of these terms has an x in them. So I could pull an x out. And actually, they each have like a factor of 2 as well. So maybe I'll pull a 2x out. So that's x squared left on the first term. If I pull 2x out of this, I'll be left with 5x. I pull 2x out of that, I'm just left with minus 6. Whoops. Okay. Still have x plus 6 on the bottom. Okay, and then I can do some actual like cool factorization here. So I still have the 2x. This is still x plus 6. But I can factor this into something. Does anyone know what numbers I would put here and here to factor that expression? Plus 6 minus 1, thank you. Okay. From the chat box, good answer. So plus 6 minus 1. Okay, I'm not sure how much factoring will actually come up on the final, but it's a handy tool to know how to do. So that is correct. And then the nice thing is these terms just totally cancel. And so I'm left with a derivative that's much simpler than what I started with. That's 2x times x minus 1. And I'll go ahead and multiply it through. So distribute this 2x. 2x times x is 2x squared. 2x times negative 1 is negative 2x. Okay. And then from there, it's kind of a cakewalk. Apply the power rule. So bring the 2 down, subtract 1, and we get 4x for the first term, minus 2 for the second term. Right, so I'll put that all in view. Any questions on part A? Oh, somebody asked in the chat, will you be posting this video to be able to review later on? Yes, I will. but I do appreciate people hanging around, so I feel like I'm not talking to myself. Okay. All right, if there are no questions, I mean, if there are questions, I'll gladly go back, but let's move ahead to part B. So part B is asking for the second derivative. So be careful you pay attention to the notation. Sometimes it's easy to miss those twos of the same thing. So I don't really want to have to work that out from scratch. Can anyone suggest like a quick solution where I can leverage what I did before?
Wouldn't it just be 4?
Yeah, okay, so that comes from here. We know what the first derivative is, and the second derivative is just the derivative of the derivative. Okay. So this is the point where I say, okay, don't do more work than you have to. Leverage what you figured out in previous problems if you can. Okay, so derivative there is 4. Cool. And let's go ahead to part C. Part C, zoom out. So we're asked to find g prime of pi. Okay. So what is that? It would help to first figure out what g prime of x is. So just find the derivative and then plug in pi. So we know g of x is x plus 6. The derivative is just 1, right? So then what is g prime evaluated at pi equal to?
It would just be 1.
It's just 1. Okay, I'm putting some like trick questions in here because these are the things that like people don't think about very often and they might trip you up on the final. But yeah, this is literally saying g prime is constant. No matter what x value I plug in, I get 1. Okay, and pi is just a number. If I plug it in, I get 1. Cool. All right, I'll give like a little bit for questions if there are any. Feel free to use the chat. Okay, cool. So let me just write up here the moral of this problem. Maybe there are 2. One is simplify algebraically before taking a derivative. That's a huge moral. And it's supposed to be an exclamation point. The second moral is going to be use previous parts if possible. Right, so part B was easy because we figured out part A. Okay. Cool. So number 3. So more derivatives. Again, I'm trying to make these kind of similar to the ones Daryl asks. So note p is a constant. I'm going to put that in a box. And we're being asked for the derivative of p times x to the p. Does anyone have a suggestion or just an answer for what that would be?
P squared times P minus 1.
Cool. So p squared, and then the power becomes p minus 1. Right. So it's the same story as before. Right. You bring the power down, so it multiplies the coefficient there, and then you subtract 1 from it. People just get confused sometimes when it's letters floating around instead of numbers. But that is correct. Okay, so that's a warm up. Now we'll see about this. I like using pi whenever I can. Okay, so let's go term by term here. So can someone tell me what the derivative of the first term is?
10pe to the power of 2px.
X. Yep, that kind of looks like a K, but it's an X. Cool. Okay, so same story, right? Bring this coefficient down. So 5 times 2p is 10p. And then leave the exponent the same. Awesome. And then we get to here. Oh, my tablet has low battery. What is the derivative of p raised to the pi power?
Will just be 0.
Awesome. It's just 0. Okay. The logic there is p is a constant, pi is a constant. I might not know what number p to the pi is, but it is just a constant, right? It's just a number itself. I'm going to put the tablet in. How about pi to the p? The last
Will
term.
that also be 0?
It's also 0. Awesome. So I'm trying to save you guys as many points as possible because I know a lot of people. Oops. Sorry about that. A lot of people will mess that up. So it's literally just the first term. The other terms are constants and they go away. Okay, let's do part C then. Derivative of this thing. 2x minus p, x plus 3. Again, I'll mention, if you've taken calculus before, you might think, ooh, that's a product of functions. And there's a fancy thing called product rule, which, again, I don't think we've learned. So stray away from that. And what's our only option if we can't use that?
Multiply first.
Yeah, just multiply it out, see what it becomes. So I'll say because I foiled, because Daryl likes when I write stuff. Right, okay. Maybe I'll just say here derivative of constant equals 0. Okay, cool. This was, yeah, good. So we'll multiply it out. So 2x times x is 2x squared. 2x times 3 is 6x. Negative p times x is negative px. And negative p times 3 is negative 3p. Okay, so feel free to write more steps if you need to. But that should be okay. We don't really have to combine like terms or anything. We can just take the derivative, just go straight into it. So the derivative of 2x squared is 4x. Derivative of 6x is 6. And what's the rest of it?
Wouldn't it be negative p and then 0?
And then 0, awesome. So remember this term is a constant. Okay, derivative of a constant is 0. Cool, yeah, so that is good. So I could have just written 4x plus 6 minus p. Yeah, don't keep the zeros on here in your final answers. Actually, yeah, I'll keep that crossed out. Cool. All right, any questions on any of these? Take a drink of water. We are a quarter of the way through our time, which I think is a decent pace. I might be able to get to some of the practice finals Daryl posted at the end if we have time remaining. Okay, we'll go ahead. Problem 4. Consider this function written in a weird way. Part A says, for what value of x is the instantaneous rate of change of f of x equal to 6? So who remembers this terminology? What's a short way of saying that?
That's derivative.
Awesome, that's derivative. So anytime you see that pop up, just be ready to take a derivative. So I'm really asking, so here the question is, when is f prime of x equal to 6? Okay, so let's go ahead and take the derivative. So f prime is going to be, I'm sure you guys know this, so I won't ask you. The derivative of 2 is 0. The derivative of negative 6x is negative 6. The derivative of the last term will be negative 6x. Okay, and I'm asking when that's equal to positive 6. Okay, so I can just solve here. Add 6 to both sides, divide by negative 6. Okay. Awesome. Then a slightly more interesting problem. Part B. Find the values of x and y corresponding to the maximum value of f of x. So how do we find, just in general, how do we find a maximum or a minimum value of a function?
Set the derivative equal to 0.
Awesome. So my idea is set the derivative equal to 0. Okay, we know the derivative already. F prime of x was negative 6 minus 6x, which we're going to set to 0. And again, just a bit of algebra. I'll get negative 6x equals 6. X equals negative 1. So that's from adding 6. And again, dividing by negative 6. Okay. Cool. It also asked for the y value. So that should be fine. And then the y value is what I get when I plug in the x value to the original function. So sometimes students plug it into the derivative because they have it sitting there, but keep in mind, if I have an x value and I want to know the y value, I have to plug it into the original function. So f of negative 1, I have to zoom out, see what that is again. So that's 2 minus 6 of negative 1 minus 3 times negative 1 squared. Okay, so that's 2 plus 6 minus 3, that's 5. All right. Any questions so far? All right, then, equation of tangent line. For that, we'll need two things. We need the slope. We're asked to find this equation when x equals 2. So we'll note that we've already done some of this work already. So again, use what you can. We know from previous work that when x equals negative 2, the derivative is positive 6. Okay. So prime equals 6. Okay. So that's fortunate. And then I just need to say, okay, y equals mx plus b. We know m is 6. From that comment above. And we can just start plugging in whatever we want for x and y in order to figure out what our y-intercept is. So let's see. We're looking at x equals negative 2. So I could plug that in. When x equals negative 2, y equals, okay, again, I just have to plug in something. This time I can't leverage anything I've done in the past. I just have to start from scratch. Kind of ran out of room there. Okay, and that's 6 plus 12, or sorry, 2 plus 12. So 2 plus 12 minus 12. Okay, so I think that's just 2. Correct me if I make any arithmetic errors, by the way. It could definitely happen. Okay, so we'll plug in x equals -2, y equals 2. So y equals 2, x equals -2. And we can solve for b. Put that in a little box. Sorry, it's kind of trapped. We'll zoom in. There we go. Okay, so that's b equals 14, I believe. So I can just come up here and be like, okay, that's 14. How does that look? Did I make any silly arithmetic errors somewhere? Okay, awesome. Thank you for the input from the chat. Okay, so I'll just put this all on the screen so you guys can see. And we'll say, again, there are a couple morals. One is know the different meanings of derivative. That it's instantaneous rate of change, it's the slope of the function, it's, well, the slope of the tangent line, it's the limit of some difference quotient, which I don't think is going to be stressed a lot, but yeah, we'll just say no different meanings. And then 2, again, use previous parts. Cool. All right, we will soldier on and get to our first word problem. Okay, so I wrote this one myself. A trebuchet sits on the ground and launches a boulder at a castle. Okay. So we have some kind of thing here, launching a boulder at some castle. Maybe I'll put some crenellations in. Okay, cool. There's my castle. And we have some questions. Okay, so first of all, we're given the height of the boulder as it soars through the sky. And we're told that 7 seconds after it's launched, it actually lands on top of the castle. Okay, so we're going to assume this is like ground level. So it starts at height 0, or I guess it starts at height. It doesn't start at height 0. We could figure out what height it started at if we plugged in t equals 0 into this equation. Right, you would get 3. So really the basket of the trebuchet is like 3 meters off the ground, but I don't think that's asked anywhere. So let's go ahead and do part A. So part A asks for speed. And well, I'll ask for participation from you guys. I know that h of t is given. So I'll rewrite it here. How could I figure out speed from this equation?
Find the first derivative.
Yeah, right. This is sort of like position. And then if I look at the first derivative, it'll be velocity. Okay, so the derivative is this. And how would I use this to get the speed when it hits the top of the castle?
You know that t equals 7, so you would just plug in 7 for t.
Cool. Oops. Okay, so I get my answer. That's 8 minus 14 is -6. Any thoughts about that?
Speed can be negative, so the speed would be 6 meters per second, I think.
Awesome. Okay, so speed is, I could say, the absolute value of velocity. So Maria is correct. In this case, it would be +6. And if we were to include units,
No.
yeah, I didn't say what t was measured in, but we'll say seconds. Actually, yeah, I did say 7 seconds. Cool. Okay, awesome. Part B says how high above the ground is the top of the castle here? So what height is this? How would we figure that part out?
Plug 7 in the original equation.
Awesome. Okay, don't get stumped by stuff that's actually super quick. We know that the boulder lands atop the castle at time 7, so if we have a function for the height, we might as well use it. Okay, so that's 3 plus 56 minus 49, whatever that is. It's 59 minus 49, so I think that should just be a nice 10-meter tall castle. Kind of short. Okay, and then how do we figure out how high above the castle the boulder flew?
Wouldn't you find the maximum?
Yeah, so like that would be our max wherever that is.
Or whenever the derivative equals 0.
Cool. So that's what I'll put for idea. Set derivative equals 0 and solve. Okay, luckily we have the derivative. That's just the velocity, right? So I could write v of t here, or I could write h prime of t. Either way, it's 8 minus 2t. We're going to set that to 0. Okay, so 2t equals 8 means t equals 4. Cool. So that's the time when it happens. So this is time t equals 4. But that's not the answer to part C. How would I get my answer?
You would plug it back into the original equation.
Cool. I'd plug it back into the original equation, and I'd make sure to note this thing in italics. We're asking how high above the castle. So we're asking for the difference in these two heights. So I'll say height above castle. There are a lot of little sneaky things that you might miss if you don't read the problem carefully. So that'll be h at time t equals 4 minus, I guess I could say minus h at time 7, because that's when the boulder hits. We know h of 7, of course, from the previous problem. Part B told us h of 7 was 10. Okay, and then I just have to figure out what h of 4 is. So okay, I have h here. If I plug in 4, I get 3 plus 8 times 4 minus 4 squared. And then that's all minus 10, because that's the height of our castle. Okay, so that's 35 minus 16. Again, hopefully I'm doing my arithmetic correctly. That was not supposed to be an equal sign. So it should be 9 meters above the castle, if I did that math correctly. All right, questions, complaints? Let me know if I did my math wrong. Okay, how much time have we eaten into? Oh, good, we're not even halfway. All right. So let's continue on. Next one. I like this one. Okay. A circular pool is 3 meters deep with a radius of 10 meters. Oops, blue for the pool. I guess it's more squat than that. Shallow but wide. Okay, so that's our kind of circular pool shape. And I'm told that it has a radius of 3 meters and a height of, or a depth of, sorry, I got that backwards. Radius is 10, height is 3. It's 10, this is 3. Cool. Initially, there's a 1 meter deep reservoir of ice cubes in here that I could sketch in like so. Okay. And heavy cream is pumped into the pool at a rate of 10 cubic meters per hour and then churned to make ice cream. So I think we all could use a pool of ice cream right now. So let's go ahead and figure this thing out. Part A states, what is the total volume of ice cream after T hours? Here I'm assuming the second heavy cream hits ice cubes, it forms ice cream. Okay, it's like instantaneously mixed and it starts out really icy, but we'll still call it ice cream. Okay, total volume. Any ideas what we could do there?
The volume formula is height times width times length.
Let's see. So it's the way I think about these is in general for like any of these nice shapes, the volume formula is always base times height. So you're not often told that. Usually you're taught all these different ones. In this case, the base is a circle. Okay, so what's the area of a circle? Well, it's pi r squared. And the height, maybe I'll call h. So yeah, the volume of a cylinder comes from the fact that it's a circle being extruded upwards in space. Right, it's a circle, and then I have a bunch of circles just stacked together, sort of. Okay, so yep, the base times height trick just works here. And how can we use that to get the volume after T hours?
You can substitute the height with 3 and the radius with a 10.
Cool. Okay, so that'll give me like the volume of ice cubes to start with. So pi 10 squared times 3 is going to be the volume of ice that we started with. Or sorry, not times 3. I think you said it correctly, times 1, because initially this is, the ice cubes are 1 meter deep. Right. Okay, so that's the volume of ice. And then what do we have to add to that to get the volume of ice cream after T hours have elapsed?
The volume of the heavy cream that's added.
Yeah, awesome. So the heavy cream goes in at 10 cubic meters per hour. So if I just add 10 times T, this component is the volume of the cream that we're pumping in. And so in total, that's what we get. So yeah, we're starting with some base volume and then we're adding 10 cubic meters every hour that passes. Cool. Oops. All right, after T hours, what percentage? Okay, so no calculus yet, but after T hours, what percentage of the ice cream is made from heavy cream? So this is sort of in line with like a paint mixing problem, except maybe not as hard. How would we figure that out?
Would it be like 10t over and then 10t plus pi 10 squared
Awesome. So if we're asking about the percentage,
times
that's
100?
yeah. If you work that out, that's 100. Yeah, maybe I'll write this out then. That would have been 100 pi for that first part plus 10t. Okay. So yeah, the percentage is just going to be the volume of cream over the total volume of ice cream at that time, which is, okay, we already highlighted what the volume of cream was. And the total volume is just our answer from before. Awesome. Keep in mind not to put the volume of the entire pool. It's asking for the percentage of the ice cream, not the percentage of like the whole pool itself. Okay, C, how many hours will it take until the pool overflows? The moment it overflows is when the pool is full. So I could ask, equivalently, how many hours will it take until the pool is full? How would we figure that out? It's like an equation I could say in words.
Wouldn't you find the maximum, so the derivative?
Let's see. So if I took the derivative of the volume, that would tell me how fast the volume is changing. But unfortunately, this is actually like a linear equation, right? 100 pi is a constant. The 10t is its slope. So if I took the derivative, I would just get 10, which I can't really set equal to 0. So there is no point where it's like, yeah, this is why I wrote it that way. It's I'm trying to like be kind of tricky with these problem statements.
Wouldn't you just make 10t equal to the difference between the amount of ice at the bottom and the entire volume of the pool?
Cool, I like that. So that's one option. We could say 10t, that's the volume of cream. And so we could say, when is 10t equal to like the remainder of this pool?
Would that be
Right.
2 meters cubed? Or sorry, whatever the remainder is.
Yeah, the remainder would be like the volume of the cylinder with height 2. And then, let's see, the other way to think about it is just find the whole volume of the pool itself and then subtract like the ice. But yeah, it's going to get you the same answer either way. So 10t is telling me the volume of the heavy cream that was pumped in. And I want to know when that's equal to, let's just say, that. Okay, so this is like saying, actually, maybe there's an easier way to say this. Yeah, I don't know. That would be correct. The alternative is use what we did in part A. Part A tells you the volume of the ice cream. We want to know when volume of ice cream equals volume of pool. If that seems more natural, I'll write down that answer as well. So that's 100 pi plus 10t equals, and then just the full volume of this thing. So pi r squared h, my bad, keep switching. Okay, and then we solve for t from there, because that'll tell us when the volume of ice cream reaches its maximum, even though you can't exactly take a derivative. It's sort of like, let me plot this for you guys. It's sort of like, okay, here's volume, here's time, And we started with some base volume of ice cubes. We get, some linear trend where we're adding heavy cream, and then the pool starts overflowing. So the pool reaches a maximum. So like the thought was initially like, oh, I can take a derivative, but the problem is there's this like kink in the graph, and the derivative does not work for kinks in a graph. So that's why we're approaching it this other way. Right, I'm going to erase this graph, and we'll go ahead and solve. So solving here, I'll keep the left side the same. So that's 300 pi. And I subtract 100 pi, 200 pi, divide by 10. Okay, and so 20 pi is a weird number to talk about in terms of hours, but there you go. That'd be about like 60 hours or something. It's a pretty slow pumping rate. And you get the same answer over here, right? So I might as well work this out as well. That right side was 200 pi, this was 10t, divide by 10, and you get 20 pi as well. So either way works. Any questions so far? Okay, I think there's a part D. Okay, part D says, after 1 hour has elapsed, and I don't think we need the other parts for this, so I'm just going to zoom in. After 1 hour has elapsed, how fast is the volume of ice cream in the pool increasing? Any ideas for that one?
Take the derivative and plug it in.
Yeah, okay, so that's correct. Take the derivative of the volume. And so this is kind of in line with what was suggested previously by Maria. So we have our volume formula. I'll just write it down here again. It was 100 pi plus 10t. So what is the derivative of that?
10.
It's just 10. It's actually just this thing. We were told the rate from the start, right? The rate is constant, it's 10. So it's sort of a trick question, but I mean, I could plug in t equals 1. It'll still be 10 there. So either way, it's fine. Okay. Maybe I won't circle my answers. Do that. Okay, cool. So there we go. There's our pool of ice cream. Let's take like a little 5-minute break. I'm gonna go fill up my water bottle, maybe grab a snack. And then I will be back promptly at 2:30 p.m. We can keep going. I'll put the next problem up if you guys want to think about it in the meantime. All right, I'm back. And let's go ahead and get into problem 7. So problem 7 starts by saying, suppose we have some function g of x here, graphed. It's not something I could write in a nice form. I guess I could write it as a piecewise function if I wanted to. And we want to know some things about the first and second derivatives. So part A asks, for what values of x is g prime equal to 0? What does it look like to you guys? Where would we get 0 derivative?
Wouldn't it be at x equals 4 and x equals 2?
Yep. And you were saying like up here where y is 4, it looks like another one, right?
Yeah, 0.
Yep, so that's correct. We have horizontal tangent lines there, if I were to draw them. So that's good. You might be interested in this point, but again, you can't really take a derivative at a little kink in the graph like that. So this will just be horizontal tangent lines. Occur at the min and the max, right? So the derivative is equal to 0 at the min and the max. So that's x equals 0, x equals 2. Okay. A more interesting question. How about the second derivative? Where is the second derivative positive? This one's a little harder. Let me pick some points and ask you about them. How about that? So is the second derivative positive here at the max value? Or is it negative, or is it 0 at that red point? Maybe a little hard to tell. The thing to remind ourselves of is that second derivative positive means I get one shape to my graph, and second derivative negative means I get another shape. So if it's positive, I should get some concave up shape. I like to think of a smiley face because it's positive. If my second derivative is negative, I get something that's concave down. I like to think of a frown because negative. Okay, so maybe seeing that now you think, okay, like this whole region looks like it would be negative second derivative because it's sloping downwards. Then maybe like this whole region would be positive, right? And then the only question is exactly where does that start and where does it end? So looking at this, I would probably pick out like this point in the middle for where it swaps from negative, from concave down, from a frown to a smile. So that's like x equals 1. Okay, so this is G. So G double prime is positive when, well, I could say when x is greater than 1, maybe. Right, so 1 is right here, so on that whole portion of the graph. And then I would have to think, does it ever stop being positive? So does it go on forever, that it's always positive second derivative no matter how far I go to the right? Or does it stop being positive? What do you guys think?
Doesn't it stop at 0.3?
It does, yeah, it stops, and sorry, it's hard to see the numbers. That's 3, but yes, I know what you meant. And it stops being positive because what is the second derivative of a line? Like what's the slope? What's the, yeah, okay, I'll just say it that way. What's the second derivative of a line?
Wouldn't that be 0?
It's 0, right? The first derivative is the slope of the line, which is a constant. And then if I take a derivative of that, I get 0. So I should say it's really when x is between 1 and 3. Okay, so that just comes from this idea. Whoops. Keep that one up. So yeah, we started here, we ended here. On that whole portion of the graph, we're concave up, positive second derivative. Cool. All right, so I'll say note second derivative of line equals 0. So not positive, just 0. All right, part C asks what is, here I'll just get part C up here, zoom back in. What is G prime of 4? What do you guys think? So 4 is here. Yeah, it's just 1, right? It's the slope of the line at that point. G prime is 1 for any value past x equals 3, really. Okay, so again, don't get scared. G prime of 4 equals 1 because slope of line is 1. Awesome. All right, you probably will get a question like this, so it's good to be comfortable with that sort of thing. Also, if he asks you where is like G prime positive, that would be wherever the function's increasing. So in this case, it's like everywhere except that middle portion. And if he asks you where the derivative is negative, it's where the function's decreasing on that middle portion. So maybe review a couple of those if you're rusty at your derivative interpretations, but hopefully that's okay. All right, let's go on to problem 8. Okay, so this is kind of a classic optimization problem. So we'll take a minute to read it over and draw a picture. I'll keep with green. A rectangular field is being constructed. Okay. So we have some rectangle. The field is sort of to be surrounded by a fence. Maybe I'll draw that in black. Okay, they don't tell us which sides are surrounded by the fence, but maybe you can think about why it doesn't really matter in the end. It'll work out either way. And then I'm going to go ahead and label my sides. I'll say this is X, this is Y. And we know that there's 400 meters of fencing available to use. Okay, so first of all, let's translate this thing. So okay, this is some field, 400 meter of fencing. How could I write an equation for that before I even get into parts A, B, or C? Based on this diagram.
X plus 2y.
Awesome. Okay, so perimeter is x plus 2y, right? Because we're not concerning ourselves with this leg of the, or that side of the rectangle. We don't need fencing there. So x plus 2y equals 400. That'll be useful to know. So part A asks for the maximum area of this field. So I'm allowed to deform it and, you know, squish it or shrink it or stretch it. But I want to find what the maximum area is. Okay, so of course area is going to be x times y. But I can't take a derivative here, right? Let me write this out. My idea whenever I see find the maximum something is take derivative, set it to 0. But this thing that I want to take a derivative of has 2 variables. So how can I get around that?
You can make another equation and solve for, like, using the perimeter equation, you can solve for one of the variables and then plug it back in, like in terms of one of the variables, and then plug it back in.
Awesome. So yeah, I will take, maybe I'll solve for x, right? So I'll solve this for x. So that would get me x equals 400 minus 2y. Okay, so 400 minus 2y is the same as x. And I'm still multiplying by y. Cool, I can then distribute the y. So 400 times y gives me this. Negative 2y times y gives me negative 2y squared. And then I can set that equal to 0. Okay. So here I'm just going to note substitute. Okay, so my derivative then is just, well, what is my derivative? Someone want to tell it to me really quick?
400 minus 4y.
Awesome. Okay, and then we're going to set that to 0, and this works out really nicely, right? Like that's 4y equals 400. Actually, probably running out of space. Let me put this up here. Implies 4y equals 400. Implies y equals 100. And presumably we can also figure out x if we have that. So now we know y equals 100. That means this side is also 100. And we would have 200 left over for x, right? Because the total perimeter has to be 400. So I'm going to erase those and just write it here. X is 200. Okay, so then the maximum area is just, well, it's x times y. So it's 200 times 100, just 2 with 4 zeros after it. Square meters. Any questions so far? Okay, along the way, we actually figured out part B, so we don't have to worry about that. The longest side of the field is actually just x, and we know that's 200. Okay. There's an alternative way to solve part A where you don't figure this out, and so you have to do a little bit of work in part B, but we did it. So longest side equals x, which is 200 meters. Okay, and then more interestingly, what if we instead wanted to maximize the area of the field while enclosing it with fencing on all 4 sides? What shape would the result be? So if I did put fencing here, does anyone have any intuition about what the shape would be? If we wanted to maximize area? So it's actually going to end up being a square. And once you see a lot of problems like this, it starts to feel natural. The idea being, okay, if I have to put a perimeter all the way around my shape, but I still want to maximize how much area there is, okay, if I did some shape like this, sure, the area might still be, or sorry, sure, the perimeter might still be 400, but now the area is like super tiny. Or I could stretch it the opposite direction and end up with the same result. The square is going to be the perfect balance between the two. To get that, you would have to go through this process again. of saying, okay, now perimeter equals 2x plus 2y. And that's equal to 400 still, because we still have 400 feet of fencing. And then maybe solve for y again. So y is 400 minus 2x all divided by 2. So that's actually 200 minus x. And then we could solve again. So area is xy, but that's just 200 minus x. Wait, what did I do? Oh, I solved for y that time. I solved the other way last time. No big deal, same difference. So that's x times 200 minus x. And that's 200x minus x squared. Set that equal to 0 and solve from there. So I'll just say solve. Because I ran out of space. But yeah, you'll get kind of an ugly number, but it'll be the same value for x that you get for y. So it's a square.
I just want to clarify, you won't take the derivative and then add it to 0?
Oh, I'm so sorry. Did I not do that? Thank you. Okay. My brain was working, or my fingers were working faster than my brain. Awesome. So yeah, okay. That's 200x minus x squared for the area. And then a prime would be 200 minus 2x. That's what you said equal to 0. Thank you so much, Maria. So yeah, x would be 100 in that case. That makes a lot more sense. So all the sides are 100, giving you a nice 400 meter perimeter like was required. Cool. All right. You guys might get a problem that has something similar to this, but maybe there's a cost involved. But don't let that scare you. The process is very much the same. You just have to, instead of doing the perimeter, you would do like the cost of the fencing around the perimeter. But the math works out very similar. Any questions? Okay, I think, let's see, we can probably get the next problem done in 15 minutes, 10 or 15 minutes, and then after that, I can look at some actual midterm or actual final exam problems from previous years, if you want. All right, so this one's fun. I don't know if you guys have read this yet. I was kind of losing my mind last night, so here we go. This is a true fact. When Mars is at its closest approach to Earth, the two planets are about 55 million kilometers apart. Okay. Suppose the speed of light is 300,000 kilometers per second. That is approximately correct as well. And we have this situation where I am leaving Mars on a spaceship that travels at 1/10 the speed of light. So instead of 300,000 kilometers per second, it's traveling at 30,000 kilometers per second. Okay, suppose NASA sends Troy a message right when he exits the Martian atmosphere. The message reads as follows. To our most esteemed astronaut and national hero, we hope this message reaches you in time. Planet Earth is going to explode in 13 minutes unless you're able to solve this math problem. Okay, so what is the derivative of the function y equals square root of x as x approaches 0? Okay, so that's a weird one. Please hurry, our lives are in your hands. High asteroids, the people of Earth. Okay, so this comes into play for part B, or part C, I mean. But before that, we have some other weird problems. So part A asks, how long will it take the message to reach Troy? Okay, so we're imagining we have planet Earth here with all its water and its continents and stuff. Cool. That's planet Earth. And mission control is asking for help because the Earth is about to explode. So I'm just going to draw a picture because why not? And they're relaying this message. Maybe I'll be like, it's a message. Cool. And I'm over here on Mars, which is not too much smaller than Earth, if I remember correctly. Okay, so Mars is like this. Maybe it's a little orange. Cool. And I'm traveling away a little bit slower, right? So this is going at 300,000 kilometers per second. I'm going at 30,000 kilometers per second. And it's sort of like one of those problems where you have two people on a road traveling towards each other, right? I've just added some flair, I suppose. So how long it will take, how long will it take the message to reach Troy is exactly the same thing as how long will it take, you know, Darren to meet Jill if they're driving towards each other on a road. It's just things are moving a lot faster in space. Okay. So let's try to figure this thing out. I could write an equation for this. And generally, my tip is if you're just finding the point at which two things meet, it's probably the most useful to compute their cumulative speed, which in the context of physics would not make sense because nothing can move faster than the speed of light. But in the case of this problem, it'll work out just fine. So compute their cumulative speed and then see how long it takes to traverse this whole distance, which is 55 million kilometers. Okay, so for that, I would say cumulative speed equals 330,000 kilometers per second. Okay. Actually, I guess this isn't going to work. I was thinking of something else. Because, yeah, that'll tell you like, oh, maybe that would work. Would that work? Okay, we'll try it two ways. So we have that, and then we want to traverse this total distance. I think it will work. 55 followed by 6 zeros, kilometers. And so whenever you have distance and speed, you can get time, right? So time, distance is speed times time. So time is distance over speed, which in this case is 55 million. Divided by 330,000. Okay, and then whatever that works out to be. So let me figure it out really fast. So we get, yeah, so this does work. 166.66 repeating seconds. Okay, the alternative approach, which I'll mention just in case you like it better, is to think of this as a number line here, going from 0 to 55 million. And the message is traveling at this rate. So 300,000 t, where t is in seconds. And then I'm traveling the opposite direction. So I'm starting at 55 million, but moving backwards at a rate of 30,000 t. And then I could set these two things equal. You will get the same answer if you do it that way. So feel free to use that approach if you like. So let's put this on our graph. Let's say I'm like right here when the message reaches me. Okay. So this is time, keep using green. This is t equals 166.66 repeating. That's where we meet up. Okay, let me erase this just so I have room. So next step, part B. Suppose Troy doesn't see the message until 500 seconds after it arrives because he's too busy browsing space Reddit, which I hope is an actual thing in the future. Will Troy still be able to save Earth? by responding to this message in time, right? They only had 13 minutes. So that is the question. Okay, so any thoughts on this one and how you might approach it?
Wouldn't you have to subtract the 500 seconds that you from the original time?
True. Okay, so yeah, so there are two symmetric ways to think. First is I would have, okay, I had 13 minutes initially, but I have to subtract 500 seconds. And I also have to subtract the 166.66 repeating seconds that it took the message to send, right? Because they sent it and they were like, we have 13 minutes starting now, but then 166 seconds passed. The symmetric way to think about it is, well, we could just go with that, I guess. But yeah, the symmetric way to think about it is figure out like what distance I get to after 500 seconds. So 500 plus 166, that's 666.66 repeating. And so I'm there when I see the message. And then I want to, immediately send a message back at the speed of light. And we could compute whether or not I have enough time to do that. Okay, so I guess both of these will be useful. This actually equals, let's figure out what this is. 13 minutes is 13 times 60 seconds minus 500 minus 166.666 repeating is only 113.33 repeating seconds. So I only have that much time to for it to transmit. Like I have to respond instantly for it to even stand a shot. And then it has to get there in 113 seconds. So it might help to figure out this distance. How far do I have to actually send it? Okay. So to do that, I would think to myself, well, I switched to green by accident. I would think to myself, okay, distance is speed times time. I know that so far I've been traveling at, let's see. Yeah, so we'll get this distance, I guess, like how far from Mars I am right now. I know by that point, 666 seconds have passed, and I was traveling at 30,000 kilometers per second. Yes. Okay, so we can figure out what that is. And I think you get 20 million. I think it's a nice round number. Kilometers. So I've made 20 million kilometers out of my 55 million kilometer journey. Okay, so this is 20 mil. So I have 35 million kilometers to go. Okay. Million to go. And that's going to be done at the speed of light because I'm transmitting a message. But if you go ahead and divide that by the speed of light, so I'm doing that now, you get, it takes, kind of ran out of space. I'll come over here, 35 million divided by 300,000 kilometers per second gives you 116.66 repeating seconds. So what's our conclusion? Will Troy be able to save Earth? It was 3 seconds late. Okay, so Earth explodes. Sorry, Earth. I failed you because I was procrastinating. Um, anyway, cool. Okay, so that's that one solved. Any questions about part A or B?
I have a question.
Mhm.
Why did we use the speed 300,000 instead of 330,000 for part B?
Let's see. So for part B, yeah, for part B, I'm just thinking about one-way travel at this point, right? Part A, there was a message coming in and me traveling in a spaceship towards it. So I combined their speeds. But for part B, the message has already reached me. Oh, and so, yeah, I guess you might think to yourself, if I'm traveling this direction at 30,000 kilometers per second, and I send a message out, maybe the message travels faster, right? At 330, because it's like our combined speed. So I guess you need to know a little physics here and know that light always travels at 300,000 meters per kilometers per second. So I guess I left that out. My mistake. So if it could travel that fast, I would save the Earth. But alas, the laws of physics cannot be broken. So of course, you guys don't need to know that. Your problem will be people traveling in cars if you have one. But yeah. All right. Part C is kind of interesting. So let's talk about that. Part C is, what's the answer to this question? Does anyone have a guess what the derivative of the square root function would be as x gets really, really small? So I could write that out. Somebody said infinity in the chat. Awesome. Yes, it is infinity. Technically, I could write down a reason for that in mathematical terms. I could say, okay, limit as x approaches 0 from the right of this derivative is actually infinite. So you could either say that or say it doesn't exist because it's so big. Alternatively, you could kind of just look at a graph. So the square root function looks like this. And if you zoom in really close near to x equals 0, the slope gets steeper and steeper and steeper as you get closer. So you could say it approaches infinity. So cool. That's just a fun side problem that is probably irrelevant for the final. But yeah. Cool. I think a couple people had to go because they had class. But are there any questions that you guys would like me to go over from like the actual practice finals maybe, or from homework or anything? I'm gonna stop sharing the screen and I'm gonna save this PDF before I forget. If not, I think I'll pull up the 2016 final exam and we will try that out. And unfortunately, didn't leave a lot of room for work on that. So I'll just write the problems out. Okay, so here's my whiteboard. All right. So yeah, you guys can head out whenever you need to, by the way. This is, of course, optional. But let's do something from fall 2016. Okay.
Can you go over question 6?
Absolutely. So question 6. Okay, question 6 has a tank with water and oil. Okay, so these seem to come up fairly frequently, so this is a good one to go over. So initially, I'm just going to write it down. Tank contains 19 liters of water, 2 liters of oil. Then oil enters the tank at a rate of 3 liters per hour. Liters per hour. All right, part A. What is the total volume of liquid in the tank after T hours? So I'll call that V of T. So this is sort of similar to what I was doing with like the ice cream churning. We have some base amount that we start with. So in total 21 liters. And then we're adding 3 liters per hour. So 3 times T. So I could say base amount or initial amount maybe. Yeah, let me write initial. And then plus 3 liters per hour. Okay, and nothing's leaving the tank, so we don't have to worry about subtracting anything. Part B, what percentage of this total volume is oil? Percent oil. Okay, so for that, again, this should be similar to the ice cream. In general, whenever you want a percentage, you want the amount of the thing you're looking for over the total amount. So I'll say oil volume over total volume. Oops. Volume. Okay. The total volume we know from part A is 21 plus 3T. And what expression could we write for the oil volume? At a given time.
2.
Let's see, it starts at 2. So it would be 2 plus something.
T.
2 plus, it's actually 3T, right? Because we're increasing at a rate of 3 liters per hour. So the thought process here should be, this is initial oil. And again, plus 3 liters per hour. And feel free to always plug in a value of T and see if it agrees with your intuition that, okay, if I plug in T equals 1, for example, I would get 5 up here. And that should make sense because like after an hour, 3 liters have been added to the 2 liters we started with. And yeah, the total volume has increased that much as well. Does that part make sense now?
Yes.
Awesome. Let's see, then part C. How many hours until 30% of the liquid in the tank is oil? So let me write that down. How many hours till, I'll just say percent oil equals 30. Okay, so what's an equation I could write for this problem? Actually, we don't need to say it. We can just kind of look at part B. The percent oil was already solved for. Right, so always make use of stuff you did previously. So really, oops, just asking when that thing equals, let me correct one thing in part B. Since it was asking for percent, I probably should have multiplied by 100 here. I always forget to do that, and I'm just thinking about the fraction. But yeah, that's to make it a percent. Okay, so let me go over here then. So if I multiply by 100, I want that to be equal to 30. Or equivalently, I could have left this off and did like 0.3. But we'll keep it how it was for part B, the times 100. Okay, so then, I mean, once we solve that a little bit, it does become 0.3 because I multiply both sides, or I divide both sides by 100 and I get 0.3. I could multiply by the denominator then to get this. Okay, and that's a little messy to work out, to be honest. That's 0.63 or 6.3, I think, plus 0.9t. Maybe I'll let you guys finish that. Well, I can do it in my head. I've just run out of space. 6.3 minus 2 is 4.3. Divided by 2.1. I think you get like 2.04. Well, equals 2.04. Yeah. Does that look okay to you guys? Hopefully I didn't make a algebra mistake. I guess I could look at the solutions, huh? Number 6.
I got a different answer.
So Daryl wrote 43 over 21. Wait, okay, so it is what I wrote. What answer did you get, Maria?
I got 30. I don't know. I don't understand how.
30, interesting. Yeah, well, let's go through the steps then, just to make it a little more clear, because I was kind of hand wavy at the end, and I apologize for that. So, okay, we'll come over here so I have more space. So I have my numerator, and then I'm going to multiply the denominator over to this side. Okay, so that's 0.3 times 21 plus 3t. Okay, and then if I FOIL that out, okay, so I'm keeping the left side the same and distributing the 0.3 in. So 0.3 times 21. Okay, well, 3 times 21 is 63. And then I just move the decimal place. So I get 6.3. And then 0.3 times 3t is 0.9t. Oops. Okay, and then I subtract, let's say I subtract 2 and 0.9t. So I subtract the 0.9t over to the other side. So 3 minus 0.9t is 2.1t. 6.3 minus 2, if I move that over, it would be 4.3. And then I can divide both sides by 2.1. So 4.3 divided by 2.1 gives you well, Daryl wrote it as a fraction. He likes fractions, so we'll keep it like that.
I understand what I made my mistake. I forgot the decimal point and the 63.
Gotcha. Okay, that makes a lot of sense. Yep. Cool. All right. We have another 15 minutes. So does anyone else have a problem from this final they would like to talk about?
I just have a question.
Mhm.
You've got 2.03. Are we gonna have to multiply that by 100 to get a percentage?
Oh, that's a good question. So our answer is actually in terms of hours,
Oh,
because it's time, right?
yeah, I forgot.
Yeah, we had started with the percentages and then we were solving for t. So,
Okay, thank you.
all right. Any other questions? I think 8 is probably a good one. Maybe I'll try 8. So I'm going to clear this. The video will go up, so if you need to reference that, you can. Okay, so number 8 from the same exam says, a rectangular field has a fence surrounding it and a brick wall dividing it in half. So I'll draw the picture over here. Brick wall, I'll do it in black, dividing it in half. Daryl's labeled this whole distance L, this whole distance W, and yeah, it's fencing around the exterior and brick in the middle. So just say brick and fence going all around. All right, and then he tells us some cost. So fence cost is going to be $8 per meter. Brick wall cost is going to be $4 per meter. And part A is asking us to express the total cost in terms of L and W. All right, so let's think about that piece by piece. The cost is going to be the fence cost, the total fence cost, plus, we'll say, total brick cost. And can someone tell me what I'll write for the fence cost in blue?
Wouldn't it be 16?
Let's see.
Oh wait, never mind.
So we got to keep in mind we're going to cover the whole perimeter.
I forgot about that. My bad.
Yeah. So we'll think about the perimeter, and I'll make a note to myself. Perimeter is 2L plus 2W. And for the cost then, it's just going to be $8 times that. Okay, so 8 times 2L plus 2W. And then brick is easier. Brick, we just have one wall of width W, and that costs $4 per meter. So that is 4W. Okay. So let's simplify it just because why not? Let's say that's okay, 16L plus 16W plus 4W. So if I combine those W's together, 16 and 4 gives me 20. Okay, so that should be good. Any questions so far? Okay, the area of the field will be 300 square meters. And we want to express length in terms of width. Okay, for that, I'm thinking, well, area is just length times width equals 300. And so that's an equation I could solve for L. Okay, so hopefully that's not too time consuming to think of. And then we'll go to part C. Use part B to express the total cost of brick and fence in terms of the width only. Okay, total cost. So I'll just call it C, where I only want to use, what was it, width. So in terms of width, okay, well, we know from part A we have that. So I'll jot that down. And we know from part B that L equals 300 over W. So we can substitute that in for L. And we get 16 times 300 over W plus 20W. And there's a bit of algebra to do there to make that look nice. But I guess it's not too much work really. 16 times 300 is 4,800 over W, and then we still have the 20W hanging out there. Okay. How are you guys doing? Are you tired yet?
A little bit.
Yeah.
Me too. I need to get some stretching in. All right, we got less than 10 minutes to go. So I'll finish part D and then I'll do maybe a couple quick ones and then we'll be all done. And you guys will all get hundreds and it'll be great. Okay. For part D, I'm just gonna put it up in the corner and erase my little diagram here. Apologies for the flickering screen as I erase. Cool. All right, so part D. Part D is the calculus. So part D says, what should W be so that the cost is smallest? So I'll rephrase it, say what value of W minimizes cost. All right. So we already know cost in terms of W is this thing. So what do I want to do with this to minimize it?
First, you want to simplify it to be able to take the derivative.
That's a good thought. I'm tired and I almost didn't think of that. But yes, okay, that's supposed to be an 8. Let's do W to the negative first power. So I'm able to take a derivative like Maria suggested. And then let's go for it. So C prime would be, I'll bring the -1 down. So it becomes negative 4,800. And then I'll subtract 1 from the power. Okay, and the derivative of the last term, derivative of 20W is 20. Okay, and I'm gonna go ahead and write this in a nicer form. Sometimes I don't like my negatives out front, so I'll put the 20 out front and say 20 minus 4,800 W to the -2. Of course, W to the -2, I could just put in the denominator as W squared. That's a little nicer to look at. And if we want to minimize this thing, we want to find where the derivative is equal to 0. So let's do that. We'll arrange our terms more nicely. So add the 4,800 over W squared to the other side, multiply by W squared, and just give myself a little more room. Divide by 20. And it's not a very nice thing to take a square root of. You might want this simplified, so I'd have to think, can I break up 240 into something and pull that out?
It states there that you can leave the square root in your answer.
Ah, it does, doesn't it? Good. Okay, so we can leave a square root. I don't know if he wants it simplified, though. Let me look at his solution. Because you can simplify square roots. like it'll still have a square root, but you can make it look nice. Yeah, so he does simplify his. He writes this as 4 root 15. And that comes from the fact that this is the square root of 16 times. I don't know if he would expect you to know that. I'd be scratching my head for a while trying to figure that out. But yeah, then square root of 16 is 4, so the 4 comes outside. I think it's probably fine to stop there, but I don't think I'm the one grading it, so we'll see. If he was cruel and took off points, I'm sure it wouldn't be much. All right, I went kind of quick through that. Do you guys have any questions about any of those steps? All good from, okay, thank you for letting me know. And let's just do a quick derivative or something. What's a good one? Yeah, let's do, so I'm gonna erase this screen. Again, the video will go up, so don't fret if you lose something here. So let's say we wanna do 3 where we have k as a constant. And let's just look at part C really quick. So part C asks to find the derivative of x squared plus k times x plus 4k. All right, and you guys have been helping me out so much. I will just work through this one and you guys can watch. Don't have to worry about interacting for the last question. So if you've had some calculus before, you might look at this and think you can use something called product rule. And I know some people in this class have taken like some type of calculus before. So I do want to mention, we're not going to use that here. We can use much simpler techniques if we just simplify the stuff in parentheses. Okay, so I'm going to FOIL this. FOIL. So that's going to be the first 2 terms multiplied together gives me x cubed. The outside terms multiplied together gives me 4k x squared. The inside terms, whoops, here's something. The inside terms give me a kx. And then the last 2 terms, oops, give me a 4k squared. Okay, so I'm going to take a derivative here. Derivative of x cubed is 3x squared. Derivative of 4kx squared, well, I'd bring the exponent down. So 2 times 4k is 8k. And I subtract 1 from the power. It's just 8kx. Derivative of the third term, well, that's just k. And maybe I will ask for input for the final term. What's the derivative of 4k squared?
0.
Awesome. Cool. That's the only trap, right? Other than that, it's a pretty standard derivative. But that is something I'll just note, keep in mind. Any term involving k, but not involving x, will be a constant. And derivative of a constant is 0, as shown. So we really don't need to include that. That is our answer. And that takes us to 3:30. So thank you guys for sticking out the full 2 hours with me. Are there any last minute questions?
This is kind of general, but do you know if the final will be the same format as the other exams?
Yes, Daryl has mentioned that to me. So it's going to be a fillable PDF. You're going to have, I think, 3 days where you're allowed to like access it and just, allot yourself a block of time where you can work on it and fill in the answers, upload it to Gradescope. Should be the same process.
All right.
I have a question about the time. How much time is he giving us?
I don't actually know that. I don't think he said that in the email, but let me just check. The final exam. Oh, that was for a different class. Yeah, I'm not sure. My guess is it's going to be like 3 hours that you're allowed to work on it. And then probably an additional hour to like type up your answers and upload it. Maybe he'll give more time. And of course, if you have like special accommodations, we trust you guys to handle that. So allocate more time if you need it. But yeah, that's all I know. I'm sure he'll send out some more specific instructions soon.
Thank you.
Sure. Thanks for coming. It's been nice working with you guys this quarter.
Thank you.
Take care.